In this module, we're moving on to thermochemistry. So we're going to take the energy that is in these reactions and figure out how it fits. Now, we have already brought up the idea of exothermic and endothermic. We needed it for some Le Chatelier's principle in the equilibrium section. We're going to find a better way to talk about these topics and also come up with ways to determine whether a reaction is exothermic or endothermic. So a couple of examples here. The first reaction where iron reacts with O2 to make this iron oxide and it gives off heat. This is a reaction that you will be familiar with if you've ever used those pocket hand warmers or any of the like muscle therapy warmers where all you have to do is open it and expose it to oxygen in order for it to heat up. That just has some iron filings in it that when it reacts with the oxygen gives off heat and you can benefit from that heat. The second reaction is an endothermic example. So if we took something like methane, which is CH4, we would have to put heat into it to break this down into solid carbon and H2 gas. So let's kind of get an overview of energy. And you probably haven't seen a breakdown like this in a while. Or maybe hopefully you've seen it recently, but this is going to kind of place everything for us that we're looking at in terms of energy for quite a bit of the rest of the semester. So we know of energy as the ability to do work. We also know that overall, like total energy is broken down into kinetic energy and potential energy. So kinetic energy, right, that's the energy due to motion, and we've used 1/2 mv squared in Gen Chem already within the context of your time in Gen Chem. And then potential energy is related to position, and then I'm going to add the word composition. So the potential energy in the composition of a molecule is something that we will deal with. Now, the kinetic energy, energy due to motion, thermal energy falls under the category of kinetic energy. We talked about kinetic molecular theory relating temperature to kinetic energy, right? So thermal energy is a type of kinetic energy, and our measure of that is temperature. Under potential energy, position, composition, we mean the chemical bonds. So the energy that is stored in the chemical bonds, the energy that you have to put in to break a bond, the energy that you get out when a bond is formed. For ability to do work, just a reminder that work is a force through a distance. That's going to come up in a lot of the things that we do. And also, by energy, total energy, we will also refer to this as internal energy, which is the sum of the kinetic and potential energies in a system. We have used the word system before, but we can now fully define this. So for perspective, if we're going to study the movement of energy, we have to define the parts. And we split it into two things. So two ultimate categories. One is the system. This is what we're changing. This is what we're measuring. This is the thing that we look at. And then the surroundings are literally everything else. So if the system is just a reaction happening in a solution, even the solution is part of the surroundings. The water surrounding the reaction can be part of the surroundings. We will generally try to limit what we're looking at, but it's either system or surroundings, and the system and the surroundings all together add up to the universe. So we're going to start with the first law of thermodynamics. There's a 0th law, but we're going to start with the first law. This is the law of conservation of energy. It has applied to many of the things that we've done so far. Just a reminder that this is the law that states that you cannot create or destroy energy. It can only be changed from one form to another. even if the only thing that happens is something gets heated up because of a transfer of thermal energy, then that's that energy went somewhere.